Maybe coming in. We got a few minutes yet, though. All right, this, and then I think it's something to do with the building or something. It's it certainly is noisy down here with that rattling and banging. Here they come, and I'd be able to turn down the sound. There we go. All right. So anyway, I got a few news articles. For one thing, we have a couple events coming up. There's a Cyber Club next week. Before this, they want me to show them those Android vulnerabilities I did in the 128 class. So students hopefully will bring in phones and we can test their apps. And then Red versus Blue a week from Saturday. We'll finally be able to get back to that. Since all the real competitions are gone, we can get back to this one. Anyway, so those are worth extra credit if you go to them. And if you went to B-Sides or RSA, send in the information of how many days of which one you went to by email where your homework goes. It's worth extra credit, of course. And here's, hey there. So this is there's a thing I did not know about. Someone just sent me this called the California Consumer Privacy Act. When they passed the European General Data Protection Regulation, many people said other people will follow suit. And of course, California did. So they passed a privacy law. And apparently it is a big deal. Just like the European one, where it greatly changes how you treat data. I think the European one is why they have these warnings about cookies on every website now, because you aren't allowed to put a cookie on a website without having them know about it. And they have, anyway, Microsoft has added software to their Microsoft Suite Compliance Manager to handle all this stuff. So there's a Microsoft's recommendation of how to handle this. And apparently both Europe and California will now require you to have a bunch of setup here to correctly handle the private data. So we'll see what comes of it all. I know the tech giants are pushing for federal privacy regulations in America right now because they're hoping to end the California one by having a weaker federal one passed, which would trump it, which is what they usually do. And it may be seen as like evil and money grubbing, but of course the other side of this is if they don't do that, they're going to have 50 different privacy regulations in the 50 states, and it'll drive you insane to run a company. So we'll see what comes of it all. I know in the last 15 years, I don't think they've been able to pass essentially any cyber legislation of any kind. Congress has just been paralyzed on it, as far as I can tell. Well, this one's pretty amazing. A huge scandal. You pay these guys $50,000 and they will get you in Stanford or any other big school. It totally came out. They had a big conspiracy of all these people, famous actresses, a lot of Bay Area people, rich, for paying to get their kids in. They'll put you on the Stanford rowing team, even though you have no athletic ability, to get you in. And they were working with insiders at the colleges and all over the place. It's a huge, big deal. They've locked up 2 famous actresses, one of the women from Desperate Housewives and another one because they bribed people to get their kids into these colleges. So it's a big deal. And so I'd say this is a low-cost provider. So for $25,000, I could get you in City College. So you all jump on that. Anyway, the Democrats are just determined to lose. It's amazing how they'll take an opportunity like Trump and they'll lose. So Democrats have decided that they have to break up all the big companies, Amazon, Google, and Microsoft. And the big high-tech companies are generally on the Democrat side, so they seem to be determined to alienate the only friends they have. Like I say, if you're betting, bet on Trump. I think Trump's a shoe-in. I think these idiots have no chance of kicking Trump out. They seem to have no idea how to win. That's my opinion. Of course, what do I know? I didn't even think Trump could win. Anyway, I did put up a prototype blockchain voting system, and when I ran it, Trump won that, and I said, oh, this thing is no good. Anyway, so Tesla just seems to be nuts. They've changed the price of their product like 10 times in the last couple months. They've decided to close a huge amount of their sales places, and then they found out that they have long-term leases, so they can't close them, and it just seems like you would imagine, like there's just this basically drunk at the helm just making up stupid nonsense, which seems to be what's happening. So people are more and more disturbed about Tesla. They've got a desirable product that makes a lot of money, but Elon Musk just seems to be too crazy to run a big company. And so I wonder if they'll manage to boot him out, like they booted Steve Jobs out of Apple in the early days when he was doing everything wrong, and they booted Travis off of Uber. You know, if you really want a top executive to be kind of boring and reliable, like a bank president, and not just some psycho deciding to do crazy things on Twitter, that's reserved for presidents. And so Firefox has a free encrypted file transfer available to everybody. Various people are getting excited and upset about this. I thought you could already do this with messenger services and stuff. I'm not quite sure what the big deal is, but apparently they think an encrypted file transfer from point to point is a big new thing. I haven't paid a lot of attention. Maybe it is. I thought you could do this with WhatsApp and other messenger services. But anyway, so in this company is going to hold the private keys for your cryptocurrency in a supposedly highly secure vault for you. Our server racks are stored in a former military bunker in the Swiss Alps, which is nuke-proof. So this sounds a lot like every other cryptocurrency snow job. And as if somehow you're safer by handing your private keys to somebody else who puts them somewhere far away. I don't know.
On a server.
I know maybe these guys are somehow providing a good service, but I've sure heard this story a lot of times before, and it hasn't come to a good end at Mt. Gox or any other exchanges. I think you should back up your own keys. But anyway, we'll see. And so the Swiss have a e-voting system. And the problem is, this is why I brought this up with the guys at the University of Pennsylvania years ago. I said, if we can do shopping and banking online, why can't we do voting? And they explained it to me, which made a lot of sense. If you do shopping or banking, you get a receipt, and we know whose money it is. The problem with voting is it's supposed to be anonymous. So since you don't keep track of who made the vote, how do you really keep track of it? That's the fundamental problem. And that's the problem here. So the Swiss made some kind of electronic voting system, which then has some kind of shuffling step where it shambles the vote so you can't tell who voted, and then somehow still remains auditable. And it turns out that is pretty difficult cryptographically, and they fouled it up. And these guys found out their mathematics to do that scrambling was not right. And it's possible to completely forge the outcome and completely forge the signature to make it look like it's still okay. In principle, that problem has apparently been solved, although I think it's somewhat beyond what we have in this class. There's a thing called the trapdoor values for these shuffling systems that can be done, but they didn't do it right, which I'm not too surprised by. That sounds pretty complicated. Sort of like the privacy systems in coins like Zcash, which are also quite fragile. You're going to somehow lose track of who someone is and still make sure that only the right person gets the money. It's not impossible, but it's complicated. Anyway, so let's carry on with the new stuff, which is keyed hashing. So we're going to talk about methods of authentication code. Here's the point. You had hashes before, like MD5 and SHA-1, which are just a fingerprint that goes on the file. And that is enough if you're going to download a file and you just want to make sure it has not been altered. But if you want to send a financial transfer, that's when I always hear about these things, then it is not enough to just know that the message has not been altered. You would also like to know that it comes from an authorized sender. So you want it to have a private key in addition to a hash. And you could have those things happen separately, but it turns out to be popular to combine them together in these keyed hashes. So a keyed hash is typically used to make MACs or pseudo-random functions, and a MAC is a tag you attach to a message like a signature, and that if the tag matches the message, that proves both that the message came from the authorized sender and that it has not been altered. That's the idea. So it's used in IPSec, SSH, TLS. 3G and 4G do not use tags, and therefore you can alter 3G and 4G messages, and the receiver does not reject them because they don't have an authenticity tag. They do, of course, turn into noise because you alter an encrypted message. When you decrypt it, it's all random, but they are not rejected because it has no way to know that they've been altered. You can just add static to the line. So the mathematical desirable property of a keyed hashing system is that you cannot create a forgery. So if you have a message and you want to sign it, you cannot create the tag, the T that goes at the M, because you don't have the key. That's the idea. That is unforgeable, and that's the main security property here. And the typical test is a chosen message attack. We are allowed to feed in messages and see the tagged messages, and yet we still can't figure out how to tag another message without knowing the key. That's the idea. You cannot stop replay attacks with these things. These systems do not include any protection intrinsically against that. You can replay a message and its tag, and it will still be valid. So you have to add that yourself at a higher level by putting in something like a index number in the messages so you can tell if a message is out of sequence. But the protocol itself does not prevent that. Pseudo-random functions are a more strict cryptographical process than the MACs, because the output has to look random. A MAC does not really have to look random. It doesn't have to have an equal probability of 1 everywhere. That's really not important. All that it has to be is unforgeable. But a pseudo-random function would have to look random. So a pseudo-random function is a more strict condition than a MAC. So 4G telephone uses pseudo-random functions to authenticate the SIM card and to generate the encryption key. TLS uses one to generate a key material from a master secret. One thing I see a lot in the Android apps is PBK DF2 password key derivation. Number 2, that's a very common one, password-based key derivation. This is essentially the same thing as the password hashes that you put in Linux. It's usually 5,000 rounds of something like SHA-512 with assault. But it is, you can look at that as a way to create a hash value to reference later, or you can look at that as a way to create a key from a password. And they're essentially the same mathematical operation. I went to the Passwords Con combined with B-Sides Las Vegas about 4 years ago, and it was very interesting. They had people, I think, including the author of your textbook there, people from the European cryptographers are over here announcing their research results, and they talked about how right now this process of generating a key from a password is very unfinished. There are only 2 or 3 possible strong protocols. There's one called bcrypt, one called scrypt, and one called PBKDF2. And they are in current use, but none of them have actually been tested to meet cryptographic standards appropriate for enterprise class computing, like proving that they can be altered in strength as computers get faster, and they can be adapted for various uses. There's like 5 or 6 fundamental properties you have to make an enterprise class system to do something like building to a domain controller. And all these are just small systems that solve only one part of the problem. So they were invented a whole series of new, more advanced cryptographic systems that have more general desirable properties. And they talked about some really wild stuff like homomorphic encryption, where you can encrypt things, and even though you can't decrypt them, you can tell if 2 things are identical. So you could do something like index and search encrypted data, even though you can't decrypt it. There are systems that have that property, but they're very strange and expensive and not in common use yet. Anyway, so the pseudo-random function has to look random, look the same as random bits by tests, and that's, of course, stronger than a MAC. So you can make a keyed hash from an unkeyed hash. That's one way to do it. All you do is append the key to the message. So you pay the key, then add the message after it. This 2 vertical line thing, it means appending. Remember, this is what WEP did. We talked about in an earlier chapter. You just stick the first 24 bits of a nonce in front of the key, and that turned out to be pretty hazardous in those conditions. And it's going to turn out to be pretty hazardous this time, too. So you can put the key and then the message and then hash it. And that, of course, is a keyed hash in that it includes information from both the key and the message, but it's vulnerable to length extension attacks. Now, it's only going to happen if you fill a block. But remember, hash functions have a block with something like 128 bits, and then they do the blocks 128 bits at a time with an internal state that keeps updating. So if the key is 128 bits, and then I put a message of 128 bits, then I could put another M2 at the end of that, and that would be a valid hash. So I could take the hash of one message, and I could forge a longer message and its tag. I cannot calculate the tag for an arbitrary message, but I can invent some carefully crafted forgeries that are valid messages with valid tags, even though I don't have the key, and that is an undesirable property. That means it's not a strong system. You cannot say that the fact that you generated a valid tag means that you have the key. Under certain conditions, you can create a valid tag without knowing the key, and that's bad. And this applies to SHA-1 and SHA-2, but not SHA-3, because SHA-1 and SHA-2, we talked about a couple of weeks ago, have this property working on blocks and adding an intermediate state. SHA-3 is the sponge function instead, to avoid that. So here's another one. Since you just appended the key with the message and you didn't put a delimiter in the middle, the first thing I saw, that's really stupid, then you can't tell a short key and a long message from a longer key and a short message just happen to have the same characters. There isn't any delimiter between the key and the message. This is kind of stupid. So that's, again, a problem. So Blake included a keyed mode to fix this. Another fix would be to include the key's length. You could include the length somewhere so you know how long the key is. That would at least fix this problem. Anyway, secret suffix is a way to fix the length extension problem. You just put the key after the message instead of in front of the message, because now the hash of M1K is the tag for that. But if you want to make the hash of M1, M2K, you cannot derive that from the hash of M1K. Since the key is always at the end, you cannot possibly create any valid tags without knowing the key. So it does solve that problem. Yeah.
Doesn't it also have the same problem if you don't have the delimiter?
Yes, it will still have the same problem with the delimiter. You're quite correct. If you would, in this case, you still can't tell the message from the delimiter. But at least you can't, but still, if you do get a tagged message, that means the person who sent it held the key. However, if there is a hash collision, then you can create a tag collision from it. Or at least the only case where this makes sense to me is when the message is exactly one block size or an integral number of block sizes. But if that's the case, then the tag is just added something fixed to the end, so you can count the tags will collide too. So that means, now that doesn't seem to me like a big problem, but it does mean that you have to have a hash long enough that there are no collisions. And remember, that might, at first I thought this is stupid, not even worth putting in the slides, because of course all the hash functions are long enough, but that's not really true. Because remember, we're not trying to make the other kind of hash function here. We're trying to make a tag function, and it's going to turn out later on, we make ones that are much weaker to try to make them faster. Because the only requirement is they're unforgeable. So your hash function might in fact be so short that there are collisions, and that does not mean it's not used for this purpose. Anyway, so HMAC is the recommended construction. Better than prefix, putting the key in the prefix or putting the key in the suffix is HMAC. This is what the most modern strong protocols use, IPSec and TLS. And it's the only one that's a government standard. And this I've seen before, and I was sort of baffled by it. You hash several times, you hash the hash, you combine the key with two pads, and then I sort of finally understand what's going on here. You take the key and you generate two keys from it. You XOR it with an OPAD, and you XOR it with an IPAD to make two different keys. That's a what you call a key schedule in something like AES. And then you prepend that to the message and hash it, and then you prepend the other one to that hash and hash it again. And that seems a little unnecessarily complicated, but certainly it has the effect that there is no way you can reproduce this or extend it or combine two of these to make another one or anything like that. It mixes them together in a good, scrambling, baffling way. So you really have to know the key to do this. Yeah.
Is there a reason why the key hashes are prefixed if they knew that previously there was a issue with putting keys in the prefix?
As far as I know, there isn't. As far as I know, you could just as well have put them after or in the middle or anywhere, because this hash of a hash seems to me to scramble them so well that it doesn't really matter where you put it. But there may be some esoteric reason. It may also just be they did it to make it faster. You use the simplest construction because it's good enough. But this, where you hash of the key and then you hash the hash of the key with the key again, that seems really good. And by the way, the OPAD and the IPAD, one is 5C and the other is 3.6. And I found online a discussion of this, and they say those numbers are pretty arbitrary, as you might imagine. They could be pretty much anything. You just have to have some way to generate two different keys from the original key. And then you created something here that is essentially impossible to forge without knowing the key. That's all you're doing. You're just mixing the key in there in a way that it's very hard to untangle. And this is what it looks like in a block diagram. On the right, you add the key with OPAD, and then you add key with IPAD here, and it actually passes through two stages of hashing to make the mesh. So you've really made it very unlikely that you're going to find some simple way to relate M1, M2's hash to M1 and M2's hash alone with this. All right, but so this is the generic attack. This is not an attack that puts it in danger. This is the attack that which will rate its strength. Like we talk about the generic attack against other things, is something like a brute force attack where you try every possible key. This is one, if you do 2 to the n over 2 calculations, then you'll find a collision. Same, if the n is the length of the hash. This is just the same as the held hash function. So if you, assuming you have enough memory to remember them all and enough time to calculate them all, this is when you'll be able to forge a tag just by brute force, just by hashing messages until you find two messages that have the same tag. All right. And so there, since you are doing 2 to the n over 2, if your n is larger than 128 bits, then that's going to take more than 2 to the 64 calculations. And as we said, 2 to the 64 or 2 to the 72 is as many calculations as anyone has done here. If you consider the whole Bitcoin blockchain, it gets up to around 2 to the 84. So somewhere around 128 or 160 bits should be long enough to make this quite secure. All right, so I got some cahoots about this stuff. I think I've got them open. I do have them open. All right.
Oh.
What? Oh yeah, really small number, yeah.
Kirk was.
He would be pretty excited, you're right. And here he is, he's missing this opportunity.
I know. One time I was Kirk.
That's right. It's always that way. I remember when I was like 17, I took the midnight Greyhound to MIT to see if I wanted to go to college there. And on the way back, I rented Numbers Runner. He said, I've been running numbers in New York City for 20 years. And the thing is, people keep changing their number. And then always next week, that number comes up. If they stick with the same number, you'll win more. And I thought it was an interesting form of gambler's fallacy. I didn't argue with him. But of course, if you keep changing your number, then you have more chance that one of those numbers will show up after a while. Anyway. What's that?
You got a message.
I got a message. Oh, thank you. Let's see what people are saying. What is that sound? Oh, there's some pounding in the room. There's some kind of, like the pipes in the building or something keep going bang. It sounds like somebody is hitting them with a stick, but it always does that. Something to do with the heating or water system around here. Yeah, pretty ridiculous. But you know, this is why I can get you in for just 25 grand. It's cheaper around here. So, all right, I'll wait a few more seconds. This may be all there are. Apparently so. Okay. The few, the proud. So which one of these lacks a Mac? (4G) telephones don't have any message authentication code. What's the most successful attack against a Mac? Replay, okay, they have no protection against replay. Which one of these is not vulnerable to length extension? Okay, good. All right. And which one is vulnerable? Secret prefix is the one that has this problem because the secret is in the hash or the short message that you already have, so adding more message to the end can be calculated from it. All right. So I've got Caitlin and M. I know who M. Hinojo is. And dude, man, you'll have to tell me who they are. That's you? Okay, good, good. Okay, I know who that is.
That is an awesome name.
Yeah, yeah.
Sorry.
That's a good name. Yeah. Okay, so let's pick up here. So talk about block ciphers. And I guess I'm going to make this a little smaller so it fits on this moderately defective but inexpensive protector we have. So, all right. There, that should do it. Now I have to figure out how to operate this thing. Good. All right. So, one thing, as you probably noticed, what a lot of people do for all cryptographies is just take an existing system and modify it. Now, this has the advantage that you can prove it's as secure as the previous system. It also means you're probably wasting a lot of computer time doing a complicated function you don't really need, and that's the case with block ciphers. So you can take SHA-256 and you can make it from a block cipher. CMAC uses only a block cipher. And so here's how CBCMAC was an improvement, was the early system. CMAC was the improvement. So here's cipher block chaining that we've been talking about. You feed an initialization value, you encrypt blocks of text, and you end up with many blocks of ciphertext. And CBCMAC, you use an IV that's always equal to 0, and you only keep the last block. Because remember, the first block is used as the IV for the next, and the next used the IV the next. So that last block down in the corner depends on everything else in a simple way. So this is one way to use a whole block cipher just to create a tag. And so that might be all right. It's kind of obvious that this is a whole lot more work than you ought to have to do, but it will result in something that does depend on everything. And that's the system that was used to make tags in CBCMAC. The problem is it's got a trivial flaw. If I feed in 2 single block messages and I calculate the tag, it's just 1 round of encryption with a key, and there's no IV. And therefore, if I consider this message, M1 and M2 XORed with the tag, because like I said, the problem with all cipher block chaining attacks is that this operation, in fact, where you take the output of one block and you XOR it with the plain text, this operation is too simple. It's too easy to review, too predictable. This turns out to be the weak spot, where you take the output of one block and combine it in a very simple way with the next block. That is a problem many, many times over. And here it is. I take the first one, I encrypt it, then I XOR it here, so I can take the message and XOR it with that, so that will undo it. And now this is just M2 going through a round of encryption. So this combined message has a tag equal to the tag of M2 alone. So I can construct a message and a tag without knowing the key. And that violates the whole security scheme. So this is broken. Just like the ones that allow length prefix, it fails the fundamental test. I should not be able to generate any message and a valid tag without knowing the key. So that's the game. So to fix it, you do the same thing we talked about before. You just use key to create 2 keys, K1 and K2. And then you use the whole key in every block, but you use just K1 in the last block or K2 in the last block. And now the last stage is different, so you can't combine any of these stages to simulate it. That's all you need. And so they use, for some reason, they don't always do it the same way. If the message fills the last block exactly, you use K and then K1. If you need to pad it, then you use K and K2. And there's a key schedule like before where you somehow calculate K1 and K2 from the key. And I don't think the exact details of how you do that really matter much. So that's CBC MAC. All right. And then, but of course, even this is a waste of computer time. You've taken this long thing of cipher block chaining, which is far more computation than you really need, because it was designed for a more rigid construction where you were not going to be able to decrypt the message. So you might consider, what would you really need to do this? Make a design just for this task to try to make it as efficient as possible. And so you can do this with things like this. Poly 1305 is a hash function. This is intended to run really fast, and it's used, Google, for example. Google invented QUIC and various other protocols. Google was the first company to switch everything to HTTPS. This is how I got on the wall of sheet back at this time. When I went to DEF CON about 10 years ago, I used Gmail, and I got hacked because Google did not use HTTPS all the time. They used it only when they're sending your password up. And once you're in, they'd send a cookie in plain text to identify who you are, and someone could steal that cookie off the wire and get in your account. And they got in my account. And Google was the company that first decided to move everything to HTTPS. And everyone at that time said it would be very expensive to move to HTTPS because the cryptography would take so much CPU that you'd have to pay for twice as many servers. That's what people believed. And Google was the only company to take the bold step of moving to 100% HTTPS. And so they got very motivated to make HTTPS faster. And this is one step where if you're going to do something ridiculous like cipher block chaining just to create a tag, that is the kind of stupidity that makes you have to pay for too many CPUs. So they said, let's make something faster. And so what you make is a universal hash function. A universal hash function is not collision resistant. It is just that when you combine it with a secret key, it is unforgeable, which is a much lower cryptographic requirement. So you could use a much simpler system, much faster to calculate, and still have what you really care about, which is that if you don't know the key, you can't make the hash, even though it does not have the property like MD5 and SHA-1 that it's hard to find 2 messages that hash to the same value. So that's the game here. And so this is all you want. For a random K, you cannot forge a message, which is not the same thing as saying you can never find a collision at all. So this is what you have. You have a sort of a mathematical function that is a polynomial taking the key to various powers and combining it with the message, chunks of message. Anyway, you can only use the key once. If you use the same key for 2 different messages, then there will be 2 functions that someone can use to solve to derive the answer, just like you have in the projects. You can't even use the same key twice for things like one-time pads. So this is you can build a hash from a universal hash function this way with your universal hash. You have a key 1 and a key 2, and you hash one part, and then you add it to a pseudo-random function based on key 2. And the keys are, and so if you have 2 keys and a nonce, you can create something that has all the desirable properties because the pseudo-random function adds the randomness and the universal hash hashes the message. This is a common trick we're going to see in all these. You use two different cryptographic processes and combine them so you get the strength of both of them. That's the idea. So this will be secure if you have a universal hash and a secure pseudo-random function, and you only use each nonce once. And of course, you have to have a long enough output that you can't just brute force it. So poly 1305 has to be combined with a cryptographic function, and here they combine it with AES. Then you take it mod 2 to the 128. This turns out to be very fast. Even though it uses AES, it only does one block of AES because you do not encrypt the message with AES. All you do is encrypt the nonce with AES. And the nonce is short, and you have a key here. You encrypt them, and the message you run through this poly function, which is very fast because it's much simpler than a cryptographic function. So this is very fast and cheap. And then there's another issue. This is the original hashing. When I taught a class many years ago, like second college class I ever taught, they said they were going to cover hashing. The hashing is a big issue in normal computer science, totally outside security. If you have an issue like trying to sort a large database, or even distribute a database across many servers, the way we're trying to do with blockchain protocols, you have to somehow break the data up into segments. And it turns out that the way to do that is to make a hash function of the data and use that to sort of randomly distribute it across these things. It's the fastest way to make things search. And that's the simple kind of hash function. And it turns out that there are denial of service attacks against those hash functions. You can send certain kinds of data up to computer systems that cause it to all hash to the same value and therefore put all the work on one of your processors in your distributed system and that sort of thing. So that's what SIP-hash is designed for. SIP-hash is designed to resist denial of service attacks targeting a hash function that is used to perform sharding, to split a job into pieces, which is a big issue in a lot of computer algorithms. So this is designed for short messages, less than 128 bytes. It's not intended to sign files. It's just intended to sort data in a pseudo-random fashion. And so SIP-hash, as you see, is just very fast here. It has a bunch of very simple small operations with XORs and such in it to scramble the bits with the minimum amount of computer time required. That's the idea, so that you could even, that's the plan of this thing. So it takes a 15-byte message and scrambles it. Anyway, so here's things that can go wrong, of course. You can have side channel, leaking out information. The most common one people talk about is a timing attack. You can also do it with emitted radio, with the power consumption, with bits that are dropped. The consequence of having an error somewhere when you lower the power supply voltage. There are many ways. The hardware implementation of some sort has a defect that leaks out information. And the most common one, of course, is what you see here. You write efficient code. So it's trying to see if the MAC is correct of the signed message. So it now calculates the MAC, and then it tries to compare it. If the first character matches, it tries the second character, but if the first character doesn't match, then it quits. I'm done, this doesn't match. So certain mismatches are faster than other mismatches. And that means you have some information about the key leaking out. That's the problem. You have to write inefficient code to avoid timing attacks. The whole point of writing code is to not waste your time doing unnecessary calculations. But if you do that, you leak out timing attacks. So you can write constant time code, which always wastes a bunch of time, always taking as long as the worst case, even when you could have done it faster, which is the opposite of what everyone learns how to do in programming. Anyway, then there's sponges. If you were to leak out the internal state, remember things like MD5 and SHA-1 and SHA-2 have this internal state, which you then add another block and change the internal state. If you somehow leaked out the internal state, of course, then you could forge the hash. And so this is a problem. And there are some functions like Blake2 that are not vulnerable to this. I think leaking out the internal state is a pretty extreme side channel, but it is an issue to talk about. Anyway, I got some more cahoots, and that's it for that stuff. All right, well, we're back to the normal numbers. Well, there is no parent sequence. See, they're apparently using SIP-hash or something to generate that number. It appears to be a effectively pseudo-random function. Logically, they should be using hash function to generate that number.
There's less than one game at any given time. You probably get a big cluster of computers connected every game.
There you
Working
go.
with players and
That might be why they're pushing me to pay $1 a month, because they're having to pay for all that. All right, I guess we'll go. Okay, so which one of these is not collision resistant? The UHF, the universal hash function, has collisions and you don't care because you add a key to it when you actually use it. All right, which one is fastest for long messages? Okay, Poly 1305 AES for long messages. These are the old slow ones that do a whole long encryption. All right. And which one is best for small messages? That's SIP hash. Looks like you got it right.
well, no, it's now present. Oh wait, no, it's not.
Everybody got it right. So somehow it turned color on you, strangely. Anyway, all right. In fact, you seem to be the second best.
No,
right.
I think I'm not going to be able to do the class.
Wait. So which one uses a block cipher, but only for one block? Kind of screwy. Okay, there we are. That's the one with AES in it. And you're in the top 3 again. So good. In fact, 2 of these people are in the top 3 again. Caitlin and M. Hinaj.
Your network connection is slow. You might experience slow.
Yeah, mine is complaining about mine too. It doesn't like the City College network very much. And Ming, which looks close enough to real name. I bet we can figure out who that is. Good. Good. That's you?
Yep.
Good. Okay, Ming's a real name, right?
Yep.
Good, good. Then my long-suffering grader will figure it out. All right, good. So let me just see if there's anything to say about projects and due dates or anything. I think in this class, things are more or less on track. This is March 12. So yeah, quiz, projects, and so on. Plenty of projects already exist. I've written the projects up to 18. All right. Oh, good. So we've got enough projects to keep you out of trouble. Okay. And I'm not sure if we're going to have a guest speaker or not. I don't think I have one coming that soon. There may be one later, but I haven't lined up any this semester. We'll see if it works out. Too many other things are going on. Anyway, I guess that's it. I'll stop the share unless anybody brings in any questions quickly. Then I'll go upstairs and see if anybody needs help in the lab. And that's it.
Nice.
Okay.
Are you going to make people show up if they have a guest speaker?